conclude today, I want to really spell out the parallels between the tree traversals from earlier and what we just did. And in so doing, I'll introduce a formal notion of graph traversals. So as you guys know, hopefully, there are many types of natural tree traversals. We saw 4. There's the preorder, the in-order, the post-order, and the level order. The preorder is you act, and then you traverse the rest of the tree. The in-order is you traverse the left side of the tree, then you act, then you traverse the right. Post-order is you traverse both sides, then you act. And then level order was a non-depth first traversal where you go in order of distance from the root. Okay. Those are our tree traversals. Now, what we just did in depth first paths is sometimes called DFS Preorder. So it's a graph analog of a tree traversal. The basic idea in a DFS Preorder is that we act before our DFS calls. It's just like preorder in a tree. So what action did we take in depth first paths? Well, we set the edge 2 value. So for example, we set the edge 2 for 1 before we ever made calls to DFS 2 or DFS 4. Okay? So the edge setting came first, the DFS calls came later. And so one valid DFS preorder for this graph is 0, 1, 2, 5, 4, 3, 6, 7, 8. That's equivalent to the order of DFS calls that are made. Okay? So you can think of the DFS preorder as the order in which DFS calls are made, and it depends, in the case of a graph, on your source. In a tree, the source is always the root. In a graph, you pick a particular source. I should note that even when you pick a particular source, a DFS preorder is not unique because we have tie breaking. That is, when we get to node 1, we might take node 4 next, or we might take node 2 next. Just kind of depends on how you do tie breaking between neighbors. So that's DFS preorder. That's a very handy notion. And what we just did is we solved the problem by setting various instance variables as we were traversing the graph. And we did so in a preorder fashion. That is, we took the actions before you made calls to the neighbors. Now you could also do post-order. We didn't do it just now, but a post-order would be taking actions after the DFS calls. So consider this version of some other algorithm where each depth first search call, it's recursive, would start by marking S, then for every unmarked neighbor, call DFS, and then print S. So in this case, the action is happening after the DFS calls, very similar to post order up here. So if you do this, the results for DFS 0 would be 3, 4, 7, 6, 8, 5, 2, 1, 0. Why? Well, because the first DFS call that finishes is 3, and then 4, then 7, 6, 8, 5, 2, 1, and then 0 is last. So you can think of this as the order in which DFS returns. And what we'll see is that both DFS preorder and DFS postorder are both useful for various tasks. So essentially, just as there are many different types of tree traversals, there are many graph traversals. We have DFS preorder, we have DFS postorder, and what we'll see is that while these are analogs of preorder and postorder, there's also an analog of the level order. And you might try and imagine what that is here before I spoil it. So the equivalent of level order, Google. The equivalent of level order is to act in order of distance from S. And in this case, this type of ordering is called BFS order, which stands for breadth first search. It's like level order. Your search is wide, not deep. So just as in level order, you start at the root and then look at its 2 children and then their children. Here, we would start at the source, 0. And then 1, which is distance 1 from the source. And then 2 and 4 are distance 2 from the source. And then 5 and 3 are distance 3 from the source, so they'll be next. Then 6 and 8, and then 7. And I've just added spaces here in order to make it very clear that 6 and 8 are the same distance. So technically, it would also be a valid BFS order to swap, say, 6 and 8, or 3 and 5. Okay? So that is the BFS order, which is another ordering in which you could perform actions on a graph. And so we'll see that that's very useful at the beginning of next lecture. So I'll just set the stage for next lecture in case you want to try and do a challenge beforehand. It's a very hard problem. But given a graph like this, try and find the length of the shortest path from S to all other vertices. Or even better, not just the length, but the actual path. So you should give a general algorithm, and there's a hint, which is you'll need to somehow visit your vertices in BFS order. So the challenge will be to do that somehow, and you'll need to use some kind of data structure as my second hint. Maybe my third hint is don't use recursion. Ugh, scary, huh? I'm a big recursion guy, but I think it's better not to do this recursively. And so we'll discuss the solution in the next lecture. And so for now, I'm just going to summarize what we achieved today. So graphs, they are a more general idea than a tree. So a tree is a specific type of graph. A tree is a graph where there are no cycles and every vertex is connected. So a graph is just the more natural notion, actually. There's a lot of key graph terms like directed versus undirected. We saw only briefly in this lecture, but we'll see much more of it later. Having a graph that has cycles versus not cycles, so that's cyclic or acyclic. And then the idea of a path and a cycle. Graph problems, I also mentioned just briefly, and we'll get some flavor for this in the coming lectures. They vary a lot in difficulty. So a common tool for solving almost all problems is some kind of traversal, and a traversal is the order in which you visit or act upon your vertices. So we had 4 different tree traversals, 3 different graph traversals, and essentially, by performing actions or setting instance variables during a traversal, you can solve interesting problems like printing out all the items in the tree or graph, or ST connectivity, or pathfinding, or many, many other problems out there like Euler paths, Hamilton paths, and so forth. So that's all I have for you today. So I'll see you next time when we will dig in and understand how to do a breadth first search.